This video we were solving a medium difficulty LeetCode problem called course schedule, and that problem was solved using the approach called topological sort, or more specifically the Kahn's algorithm. We explained how Kahn's algorithm works, and also we showed how we could use that algorithm to solve that particular problem. In today's video, we'll be solving another problem using the same algorithm, the same topological sort approach. The problem is LeetCode's problem number 329, and it's called longest increasing path in a matrix. It's a hard problem, and if you are not familiar with the topological sort and how Kahn's algorithm works, I would recommend you checking out the previous video just to get yourself familiarized on a slightly easier problem. And yeah, today we will be solving using the same approach, but to solve a slightly more difficult problem. It's categorized as a hard problem, but I would say if you see the idea, it's more like a medium plus problem. So let's first go through the description. So given an m times n integers matrix, return the length of the longest increasing path in matrix. From each cell, you can either move in 4 directions, left, right, up, or down, and you may not move diagonally or move outside the boundary. For instance, wrap around is not allowed. So let's go through a couple of examples. The example 1, here we have a matrix 3 times 3, and then with the numbers, with the integers 994, 668, 211. So the matrix is represented as an array of arrays, and here the outcome should be 4. Why 4? Because the longest increasing path in the matrix would start from this number 1, and it would go 1 step to the left and then 2 steps up. So it will be 1, 2, 6, 9. It contains four numbers. That's why the output in this case will be 4. Let's see a couple of more examples. So in the example 2, we have another 3 times 3 matrix, and but with a different set of numbers. So this matrix contains the following numbers: 3, 4, 5, 3, 2, 6, 2, 2, 1, and the outcome should again be 4. Why 4? Because if we start from the top left corner, from this number 3, and if we go 2 steps to the right, so from 3 to 4, from 4 to 5, and to 5, and then 1 step down from 5 to 6. So it's a path that which is of integers strictly increasing order. So 3, 4, 5, 6, and again it contains 4 numbers. If you would try to find any other path, increasing path, let's say from this number 1, we can go 1 step up, so that would be 1, 6. So it would be a path length with the length of 2, or if you go to the left, so it would be 1, 2. Also from this number 2, we can go up 4, right 5, down 6. So 2, 4, 5, 6 would be another valid path with the length of 4. So, but there is no a path which has the length longer than 4. That's why the output should be 4 in this case. And the third example, if we have a matrix which has only one element, so 1 times 1 matrix, the output should be 1, because we can take that 1 included into the path. So the output should be the number of numbers that belongs to the longest increasing path. And finally, let's quickly go through the constraints. So let's say that M is the length of the matrix, and or the number of the rows in the matrix. N is the number of the columns in the matrix. And here this constraint means that every row I contains n columns, meaning that every row has the same number of columns, and both m and n are integers between 1 and 200, including 1 and 200, and every number inside the matrix is a number between 0 and 2 over 31 minus 1. So even negative numbers are not allowed. So we can assume that this is always true. We can add a validation at the beginning of the solution. We can do it, but I wouldn't waste time on it. I can leave it for you. But as I always say, please make sure to clarify if you are given this problem during your interview. Please don't just assume that the input parameters will always be valid. So just at least clarify with your interviewers whether you can assume that the constraints will be always satisfied, or or not, and according to that you can implement the validation at the beginning or not. But validation should be relatively simple. You should just check whether the matrix is null or not, whether it's empty or not, whether these other constraints are satisfied. So in the previous, so let's quickly go through the method that we need to implement. Like always, I'll be using Java programming language, and the method that we need to implement is called longest increasing path, which takes a matrix or as an input to the matrix, and which returns an integer, which will be basically then the length of the longest increasing path in the matrix. So I have already explained in the previous video how topological sort works and how Kant's algorithm works. So assuming that we are already familiar with that approach, we will just see how we can solve this problem using the same technique. So let me go back to the problem description. Okay, so here is the matrix, and we need to find the longest increasing path, and we can take any node or any element of the matrix as a starting point, and for every element we can go in one of the 4 directions, so up, right, down, or left. So there diagonal moves are not allowed, and we cannot move outside this matrix. So those are the rules, and yeah, we now need to see how we can solve this problem. So first of all, why I think this problem is considered as a hard difficulty problem? Probably because it's not that obvious that topological sort can be used here to solve this problem. It might not be obvious, however, I already mentioned that at the beginning, so topological sort or Kant's algorithm will be used here to solve this problem. So topological sort, how it works, the idea of the topological sort is to find the order of the elements that can be taken in order to follow the prerequisite rules. So as explained in the previous video. So how can we do this? And topological sort works with graphs. Well, what we can do here, we can treat these matrix elements as nodes of a graph, and we can say, because we can move in any direction, but there is but the path needs to be increasing. So from here, from the node 6 or from the element 6, we can go up or we can go to the right, because both up and right are the elements greater than 6. So if we go up, it's 9. If you go to the right, it's 8. Meaning that from 6 we can go to to 8, or we can go to 9, but we can't go left nor down, because 1 and 6 are not greater than 6. Okay. And we can treat this matrix as a graph where elements of the matrix are nodes, and edges, directed edges, are between every element. So every element can be connected to adjacent element by an edge only if it's less only if it's less than the adjacent element. So here 6 can be connected with an edge, with a directed edge with 9, and the arrow will go from 6 to 9. Also there will be an edge from 6 to 8. Why? Because 6 is strictly smaller than 9 and 8. But there will be no edge from 6 to 6 and from 6 to 1. So we can assume that this is a graph and edges only exist between the adjacent nodes. But when I say adjacent, I mean the adjacent nodes are nodes that are next to the node in one of the 4 directions, so up, right, down, or left. So here, if you look into this solution path, the longest increasing path, we can assume that these arrows are actually the edges of the graph. So the longest path in this increasing path in this matrix will be equal to the longest path in the converted graph, following the rules that I've just explained. So here, these would be the edges of this graph, but there will be more edges from 6 to 8, from 6 to 9, from 4 to 8, from 4 to 9, from 1 to 8, from 1 to 8, etc. So those are all the edges, but the longest path in this graph will be actually the longest increasing path in this matrix. This graph will be directed because every edge has a direction from a smaller number to a bigger number, right? So it's a directed graph, and also the converted graph will be acyclic. So it will contain no cycles. Why? Because every edge goes from a smaller to a larger number, and because of that, there is no way we can go back to the starting node, and starting from any node in the graph, because we are always moving towards larger nodes, so we can't go back to the starting point. That's why this is going to be a directed acyclic graph. And what we learned in the previous video, if a graph is a DAG or directed acyclic graph, then it means that there is a valid solution, or we can apply topological sort. How would topological sort help us here? So topological sort finds an order following the rules, certain rules. But here, what would be the solution of this particular problem by using the topological sort as an approach? Well, it will be the number of levels in the topological sort solution. So what would be the level? let's say we will learn that topological sort starts from the nodes with in degree in degree value equal to 0. So it will start from the nodes that has no edges that goes into them. There could be multiple nodes with in degree equal to 0. And let's see from here, 1 is one of them. This one is also another node with degree 0. And we can say that those two nodes are at the same level. The number of levels will be equal to the number of the length of the longest increasing path in this matrix. So that would be basically the solution of the problem. We will see in code how we will measure the number of levels, but basically at the end of a cycle of a Kant's algorithm, not cycle but the loop in the while loop, so at the end or at the beginning, Q has certain number of nodes, or at the beginning it has, so the one level will be all the Q's, all the elements in the node, all the starting nodes in the element. So at the beginning we will just measure the number of nodes in the queue. I'll show you in the code. It's easier when we implement it in code, but basically the solution of this problem will be we will convert this matrix into a directed acyclic graph. We will apply the Kant's algorithm, and we will count the number of levels in the graph, and that number of levels at the end will be the length of the longest decreasing path. So let's start with the solution. So first let me create int m is equal to matrix dot len and int n is equal to matrix of 0 dot len. We can assume that this matrix is basically we can assume that all the constraints are satisfied. That's why I am not adding a null check or other checks at the beginning, but yeah, feel free to add them at the beginning if you want. I just don't want to waste time on it. So like the very first thing that we need to do, we need to calculate the in degree values for the nodes in the graph. So we are not going to create a separate hash map graph. There's no need for that because all the information about the relationship between the nodes is already present in the matrix. So we can treat this matrix as basically as a graph. Okay, so let's create an in degree. So here every node in the graph will be uniquely identified by its row number and column number. So in degree array it's not gonna be an array but more like an array of arrays or 2D matrix. So int in degree is equal to new int of m times n matrix. Okay, so now let's initialize this in degree, and before we do that, I'm gonna create a helper method, private void, not void but boolean valid field, that will check if a provided field is a valid field on the matrix, because we don't want to take the values outside the matrix, so the negative I and j values, and also the values greater than the size of the matrix. So we will check whether a value I j in the provided matrix is valid. So a field is valid if, so we can say return if I is equal to 0 or j is equal to 0 or I is less than matrix dot len or j is less than matrix of 0 dot len, something like this. Another approach would be to pass the m and n values. That's also doable. So yeah, maybe we can do that as well, but it doesn't matter. We can pass the whole matrix. It's fine. Maybe it's nicer to pass m and n. So a field is value. Oh, sorry, not if it's equal, but if it's greater and sorry. Let's do it in a different way. Sorry. This so we can say return if I is greater or equal than 0 and j is and I is less than matrix dot len and j is greater or equal than 0 and j is less than matrix of 0 dot len. Okay, so something like this. Sorry about that, but basically we are checking whether a node ij is a valid field or is a field on the matrix or it's somewhere outside the matrix. So we need to make sure that we are dealing only with the valid fields on this matrix. Okay, so here we initialize this integree matrix as a matrix of zeros with a length of m times n, with a size of m times n, and now we need to calculate the integree for every single element on the matrix. So for each, so for int I equals to 0 while I is less than m, I plus plus for int j is equal to 0, j while j is less than n, j plus plus. So how can we calculate this in degree for, so now we want to calculate in degree for the field eij. So what should we do? Let's say that 6 is an element we are calculating in degree 4. So for 6, in degree in 6 will be if any adjacent element out of these 4 is less than it. So here 6, 9 is not less than 6, 8 is not less than 6, 6 is not less than 6, but 1 is less than 6, meaning that there will be an edge from 1 to 6, meaning that the in degree for 6 will be 1. Why 1? Because only one node next to 6 is less than 6, so there will be an edge from that node to the node 6. Okay, so here we also need to define a matrix of valid directions. We can call it dirs. Go to new int and let's, so what are the valid directions? Valid directions are to stay on the same row but to go +1 column or -1 column, or to stay on the same column, but to go plus one row or minus one row. So there will be 4 combinations of, so it will be 1, 0, 0, 1, minus 1, 0, and 0, minus 1. Okay? So these are going to be 4 directions that can be used. So what do we need to do here? So we need to go for a field ij. We need to calculate the adjacent, all 4 adjacent nodes if they exist. So for each direction there within the directions there's int the, we can call it dx is equal to I plus direction of 0, and int the dy is equal to j plus direction of 1. Okay, so we are going to increase the inbound degree for ij element only if dx dy is a valid field, and additionally if it's strictly smaller than an ij element on the matrix. So if valid field dx dy matrix, and if matrix of dx dy is strictly lower than matrix of ij. If this is true, then in degree for ij plus plus. So if, and we will do this for all 4 directions. So for every adjacent element to the ij element, if it's a valid field, so for instance here if we are doing this for, if ij are this element, this 8, one direction would be to the right, but that wouldn't be a valid field. That's why we need to check whether it's a valid field, and additionally if that adjacent element is strictly smaller than the current element, and in that case we will be increasing the in degree for the ij for the current element. Okay, so we have initialized this in degree matrix, and now what we need to do, we need to apply the Kahn's algorithm, the topological sort. So we will be needing a queue, but this time queue will be the elements of the queue will be the type of an integer array. That array will be actually a pair, an array of length of 2 that will be a pair ij that represents elements on the matrix. So let's call it q equals to new linked list, because in Java linked list is one of the implementation of the queue interface. And now we need to initialize this queue with the elements whose in degree is 0, because if in degree is 0, those could be potential starting points. We have explained that this graph converted from this matrix is DAG, it's directed acyclic graph, and because that's true, the Kahn's algorithm can be applied to this graph, and it will cover definitely all of the elements, because the fact that it's directed acyclic graph means that all the elements will be covered. So we are sure that we will be covering all the possible paths, and we will be able to find the longest path in the matrix. Okay, so how Kahn's algorithm work? We have, as I mentioned multiple times, we covered that in the previous video. So now, as a first step, we need to initialize this queue with the elements whose in degree is 0. So what we will do, we will do for int I equal 0 while I is less than m, I plus plus, for j equal to 0 while j is less than n, j plus plus, if in degree of ij is 0. If this is 0, we will add this element to the queue. Q dot offer new int ij. Okay, and finally let's implement the while loop, and let's iterate through the elements of the graph to figure out the longest increasing path. So I'm going to create an integer size, which is equal to, or let's call it result, which is equal to 0 initially, and we will return that result at the end. And this result will basically be the number of levels in this directed acyclic graph. So while q is not empty, so we are now just implementing the Kahn's algorithm, we can say result plus plus. So we are starting, so the elements with the in degree 0 are the starting points, and they are all on the same level. And at this point, all the elements in the queue belong to the same level. But also, as Kahn's algorithm, as we will be adding more elements to the queue, those elements will have a different level. So we need somehow to make sure to distinguish the difference between the levels of the elements in the queue. And the way how we can do it, because we know that at this point all the elements in the queue belong to the same level, so we need to iterate through this queue that amount of time, which that number of times which is equal to the current size of the queue. So we can say int size is equal to the queue dot size, and we can do for each int I equal to 0 while I is less than size I plus plus. So this will just count size number of times, and we will say int element or node is equal to q dot poll. Poll will take the element, sorry, it's a 1D array. Q dot poll, it will take a node from the queue which was first added to the queue. So once the node has been taken from the queue, what we need to do, we need to recalculate or to update the in degree values for the remaining elements in the graph after this node is removed. So how can we do this? So we need to go through all nodes. So which nodes will be affected? There can be at most 4 nodes that are affected. Those are nodes that are next to this node. One node to the up, one to the one node down, one to the right, and one to the left. So let's go back to this matrix or to this graph. So if we are removing one, only nodes that could be affected are the nodes that are next to this node. So let's say that one is removed from the queue, then there will be, at the beginning there is an edge from 1 to 2 and from 1 to 6. So the in degrees for the node 6 and for the node 2 will be decremented. So what we can do, for each direction within directions, and here I'll say, do I need to, okay, int next, I will call it next x is equal to node of 0 plus direction of 0, and int next y is equal to node of 1 plus direction of 1. Okay, but this will never be null, so it's complaining about this node that can be null. The elements of this node can be null, but actually they will never be null because we won't be adding null values to this queue. So what we now need to check, we need to check if next x and next y is a valid field. So we first need to check whether next x and next y on the matrix is a valid field, and additionally, which nodes will be updated? Only those nodes that are strictly larger, that are bigger than the current node. So if you are removing one, in degrees of 6 and 2 will be decremented. So we need to check if the node, or maybe it will be easier if I have added int x equal to node of 0 and int y is equal to node of 1. So in this case I can use here x and y, and here I can check if matrix of next x and next y is strictly greater than matrix of x and y. So if this is satisfied, in degree of the next node, next x, next y, should be decremented. And additionally, if this in degree of next x, next y has now become 0, then we should add it to the queue. If in degree of next x, next y has become 0, add it to the queue. New int next x next y. And this is it. So every time, so it will, this for loop will iterate size of the queue times, so it will cover all the nodes at the same level, and it will add some new elements to the queue, and then those newly added elements will all be at the same level, one level below the starting level. So, and then we will again do the same process, size of the queue number of times. So basically that way we are calculating the number of the levels, and at the end, once we are done, we will just return the final result. And that would be the solution of this problem. Finally, let's try to test this approach. So here I have already prepared some test examples. Sorry. Okay. So here we have a matrix 1, 2, 2, 3, and yeah, this this solution is part of the solution class. So I have already initiated a solution object, and let's print the result. So before we run this example, let's just quickly see what should be the outcome. In this case, the outcome should be 2, right? Because from 1 we can go to, no, the outcome should be 3, because from 1 we can go to 2, and from 2 we can go to 3. So there are 2 valid paths with a length of 3, and that's why the output should be 3 in this case. Let's see if this works. Yeah, here, so the output is 3, which seems correct. Let's try with this example. So it should be 994, 668, 994, 668. And 211. In this case, the output should be 4. Why 4? Because if we're starting from this node 1, we are going one step to the left, 1, 2, 3. So that should be the outcome, or it's more obvious on this image. So let's try with this one. Yes, the output is 4. Okay. So that should be the solution of this problem. Speaking of the time complexity, we have already covered in the previous video that the time complexity of the Kant's algorithm is always big O of V plus E, where V is the number of the nodes in the directed acyclic graph, and E is the number of the edges. But here, let's see how many nodes do we have here. If the matrix has has m rows and n columns, then the number of the nodes will be m times n. So the time complexity will be m times n plus, and what's the number of the edges? And in the worst case, if you imagine each node can have up to 4 edges, so the number of edges will be, in the worst case, 4 times m times n, and therefore the time complexity of this solution is big O of m times n. So that should be the time complexity of this solution. That would be all for this video. I hope that you liked it, and I'll see you in the next video. Thank you.